Hello friends, this is one university question on strain energy method for calculation of deflections. This university question is for JNTU in the year April 2017. The problem data are given here. It is an L-shaped frame loaded with 4 kilonewton per meter for the horizontal arm. You can see this. This is the loading data for the frame. Portion BC is loaded with uniformly distributed load of 4 kilonewton meter and the vertical arm is 4 meters. The horizontal arm is 2 meter. The values of E and I are given. Now we will use the Castiglione theorem for calculation of vertical and horizontal deflections at point C as has been asked for. The values of E and I should be converted to kilonewton per meter square and meter power 4 respectively, so that all the dimensions are consistent. Here the length of AB and BC are given in meter. Therefore, E is converted to kilonewton per meter square and I is converted to meter power 4. Before start of the problem, I would like to tell one thing. This problem is available for free download in the website mentioned here, https://rgnsite.wordpress.com. This is available for free download. Not only this university question, nearly 500 university questions on various topics: RCC design, structural steel design, strength of materials, matrix methods, etc. And lot of explanations are made available in the form of one-word answers, questions and answers. So you can have free download of this page plus other university questions by visiting https://rgnsite.wordpress.com. Now, as per Castiglione's theorem, the deflection is equal to 1 by EI into integral m into dm by dv into dx. Now here first we will calculate the vertical deflection at point C. For this purpose, we have to introduce a fictitious load V at point C. Now for the portion BC, you take C as the reference point and write down the expressions for bending moment at a distance x from C. That is equal to 4 into x square by 2. This is uniformly distributed load plus this fictitious load V into x. So this is the expression for M for the portion BC. Then dm by dv is equal to, you have x. Because the first term doesn't contain any V, it is equal to 0, its derivative. The second term contains V. So dm by dv is equal to x. Similarly, we have to write down the expression for AB. We have to write the expression for bending moment. It is the total uniformly distributed load is 4 into 2 kilonewton. It is acting at a distance of 1 meter from this arm. So for the entire length of BA, the lever arm is 1 meter. It remains constant. 4 into 2 into 1. B is the reference point, and we have to carry out the integral for B to A. Then we have this fictitious load. For this fictitious load, the arm distance is 2 meter. B into 2. It remains constant for the entire length of B into A. So this is the bending moment due to UDL. This is the bending moment due to fictitious load B into 2. Now, what about dm by dv? The first term doesn't contain V, so it is 0. The second term contains V into 2. So dm by dv is equal to 2. Now we will apply the Castiglione's theorem. 1 by EI into integral m into dm by dv into dx. So you apply this for the portion BC as well as AB. For the portion BC, the limits are 0 to 2. C is the reference point. CB, the limits are ranging from 0 to 2. Similarly, for the portion BA,
The limits are ranging from 0 to 4. P is the reference point. By taking a section X from the reference point, we have written down the bending moment expressions. So the limits are ranging from B to A, that is 0 to 4. And this is what has been written here. This is for the portion CB. This is for the portion BA. The limits are 0 to 2, 0 to 4. This is the multiplication of M into dm by dV. This is the multiplication of M into dm by dV for the portion BC. This is for the portion AB. So the values of E and I have been calculated in terms of kilonewton per meter square and meter per 4. After substitution, we have this expression for delta V. Now, this fictitious load V should tend to 0 for getting the actual deflection. Therefore, in this expression, we have to substitute V is equal to 0. Then after simplification, we are getting this value of deflection as 0.00423 meters, which is equal to 4.23 millimeter. We have to substitute V is equal to 0 after the integration. Now, similarly, we have to calculate the horizontal deflection. For this, you introduce one fictitious load H in the direction, in the horizontal direction at point C, and write down the bending moment expressions for BC and AB. Now, for BC, the bending moment expression is 4 into x square by 2, and we have to calculate the value of dm by dh, but that is equal to 0. Therefore, the integration for the entire portion BC is equal to 0. Now, the integration should be calculated for the portion AB. For the portion AB, the bending moment is equal to the total UDL 2 into 4 into its arm 1 meter plus H into X. We are taking B, the X from measured from point B, H into X. The point is, reference point is B. The limits are ranging from B to A. Therefore, the limits are 0 to 4. This is M. This is due to UDL. H into X is due to the horizontal load. Therefore, dm by dh is equal to X, because the first term doesn't contain any H. The second term contains H into X. Thereby, dm by dh is equal to X. Now, delta H is equal to 1 by EI integral M into dm by dh into dx. Now, we have to carry out this integration between the limits 0 to 4. This is for the portion AB. For the portion AB, the limits are 0 to 4. For the both the terms, the limits are 0 to 4. Please understand. Here 0 to 4. Yes, it is correct. Here it is written as 0 to 2. It is wrong. This 2 is wrong. This 2 is wrong. This 2 is wrong. This also should be 0 to 4. M into dm by dh. This is the value for the first term. This is the value for the second term. Both are applicable for the portion AB. Therefore, the limits are 0 to 4. Here also it is 0 to 4. This 2 is wrong. Then after simplification, and you put H is equal to 0. When you put H is equal to 0, this term vanishes. Only this term will remain. And after simplification, you will get 0.0036 meter, which is equal to 3.6 millimeter. This is by strain energy method. Unit load method is also one form of strain energy method. This can be dealt by unit load method also. As I already told, this problem is available for free download in rgnsite.wordpress.com. rgnsite.wordpress.com, along with other 500 university questions on various topics such as RCC design, steel design, strength of materials, matrix methods, etc. The explanations are available in the form of one-word questions and answers. Thank you very much.